Something is moving through the deep black of the inner solar system, and in less than 2 years, it is going to make history. On June 27, 2026, an object known as 1997 NC1 will scream past Earth at a distance that has orbital mechanics experts holding their breath. Welcome back to Terra Alerts, where we break down the complex data the mainstream outlets usually gloss over until it is too late. We are talking about a flyby that hasn't happened on this scale in over 4 centuries. To put that in perspective, the last time this specific asteroid was this close to our home, the telescope had barely even been invented. This isn't just another routine space rock passing by. It is a potentially hazardous asteroid that is currently defying simple classification. Discovered back in 1997 by the Linear Project in New Mexico, we have been tracking this Amor-class ghost for nearly 3 decades. We have a high-precision orbital solution, a condition code 0, which means we know exactly where it is located, but what we do not know, and what scientists are genuinely nervous about, is the true nature of the beast itself. At 1547 Universalities on that June afternoon, it will reach its closest approach, roughly 1.6 million miles from our atmosphere. While 1.6 million miles sounds like a comfortable cushion, in the vast scale of the cosmos, it is a razor-thin margin. It is traveling at a staggering 25,700 miles per hour, a kinetic energy profile that demands our full and immediate attention. For the last 29 years, optical tracking has painted a picture of a predictable neighbor, but 2026 is when the mask finally comes off. This event is so significant that the next time it comes this close won't be until the 25th century. We are the only generation alive that will see this object with this level of clarity, and the stakes couldn't be higher. If you have a 4-inch telescope and dark skies, you will be able to see it yourself as a moving point of light. But what that point of light is hiding is currently the subject of an intense debate within the planetary defense community. You see, 1997 NC1 is currently suffering from a massive identity crisis that changes everything about our global risk assessment. Astronomers are looking at the data and seeing 2 completely different versions of reality. On one hand, we might be looking at a relatively small, highly reflective metallic stone that poses a regional threat. On the other hand, we could be facing a dark primitive titan that is far larger than anyone initially suspected. This isn't just a minor discrepancy in some academic ledger. This is a gap that changes the fate of cities. This is the difference between a regional disaster and a global catastrophe that could alter the very course of human history. Why is it so hard to pin down the size of an object we've been watching for 30 years? It all comes down to a phenomenon called the albedo size equation, and it is the reason why this 2026 flyby is more than just a scientific curiosity. When we look through our telescopes, we aren't seeing a physical shape. We are seeing reflected sunlight, a tiny glint in the infinite dark. If the object is dark like charcoal, it has to be massive to reflect that much light back toward our sensors. If it is bright like polished chrome, it can be much smaller and still look the same to our sensitive equipment. This gap in our knowledge is where the real danger lives for every person on this planet. We are essentially staring at a shadow on the wall and trying to guess the weight of the person casting it. By the time we get the radar data from Goldstone in 2026, we will finally have our answer. But the possibilities right now are haunting to anyone who understands the math. Imagine an object hitting the atmosphere that we thought was a manageable 400 meters, only to realize it is a 1.6-kilometer monster. That 1.6-kilometer mark is the global threshold. It is the point where an impact stops being a local tragedy and starts being an extinction-level event for our entire species. We are talking about the potential for nuclear winter, with global crop failures, and a complete collapse of modern infrastructure. And yet, until we get closer, we are flying blind regarding its true physical dimensions and mass. The orbital mechanics tell us it will likely miss us this time, but the physics of its composition will tell us if we should be terrified for the future. As we track its path toward that June 27th deadline, Every data point counts. We are looking at a poster child for planetary defense, a test case for everything we have learned since the DART mission. If it is a rubble pile, a loose collection of rocks, our deflection strategies change completely. If it is a solid, monolithic slab of iron, it becomes an unstoppable bullet through the fabric of our security. We are at a crossroads where the known becomes a discovered world, and the transition is going to be explosive. Stay with me as we dive deeper into the specific numbers that are making the brightest minds in NASA lose sleep. Because when you understand the albedo paradox, you will realize why 1997 NC1 is the most dangerous question mark in our sky. To understand why 1997 NC1 has scientists checking their calculations, we have to talk about how we see things in deep space. When our telescopes lock onto an object like this, they don't see a cratered surface, they see a single pixel of light. This is the heart of the albedo paradox, a riddle where the brightness of that pixel lies about the danger hiding behind it. Think of it like seeing headlights in the night. Is it a moped with high beams or a semi-truck with dim lamps? In the solar system, we measure size by combining visual brightness with reflectivity, which we call albedo. If the rock is dark, like charcoal, it must be huge to reflect enough light for us to see it. But if the rock is shiny like fresh snow, it can be much smaller and still produce that same brilliant glow. For 1997 NC1, the 2010 NEO's eyes data threw a massive wrench into our standard planetary defense models. That infrared data suggested a diameter of only 400 meters, which sounds like a relief until you look at the requirements. To be that small and look this bright, the asteroid would need an albedo of 58%. That is a staggering number, as most asteroids are dark bodies with an albedo between 5 and 20%. A 58% reflectivity would make 1997 NC1 one of the shiniest objects in the known solar system. If that small and shiny theory is correct, an impact would only cause regional devastation, leveling a city. But here is where the sensemaker delivers the cold reality that keeps the world's leading experts awake at night. If 1997 NC1 is a standard stony rock, its brightness dictates a diameter of 1.6 kilometers. That is a mile-wide mountain of rock hurtling through the void at 25,000 miles per hour. At 1.6 kilometers, we aren't just talking about a local impact anymore. We are crossing the global threshold. An object of that magnitude hitting Earth triggers a nuclear winter and global crop failure. This is the crisis of 1997 NC1, a spectrum between a bad day and the end of civilization. To make matters confusing, spectroscopy has given us 3 different chemical barcodes for this object. Some readings point toward a B-type classification, suggesting it is a dark primitive time capsule rich in carbon. If it is a B-type, it is almost certainly that massive global killer because carbon rocks are notoriously dark. Other readings suggest an S-type stony composition, which would put it at a diameter of 900 meters. Then there is the Q-type theory, which suggests the surface is fresh, perhaps scoured by extreme tidal forces. This Q-type classification is the only way the small and shining theory works, but Q-types are incredibly rare. We are essentially staring at a cosmic silhouette and guessing if it is holding a pebble or a sledgehammer. The margin for error is the difference between regional damage and a total planetary reset. This uncertainty is why the flyby on June 27, 2026 is the most anticipated event in planetary defense history. We aren't just watching a rock pass. We are waiting for the albedo paradox to be solved by hard data. Every telescope on Earth will be tasked with piercing this veil before the asteroid makes its approach. If we find out this thing is a 1.6-kilometer behemoth, the conversation shifts to a global emergency. The stakes couldn't be higher, as if our models are wrong about reflectivity. We have been vastly underestimating the kinetic threat. Imagine the shock if data confirms that what we thought was manageable is actually a heavyweight champion of extinction. This isn't just math. It's the physical reality of a mile-long bullet aimed in our general direction. We are living in a state of Schrödinger's asteroid, where 1997 NC1 is simultaneously a manageable rock and a world ender. The clock is ticking down to 2026 when that wave function finally collapses for us all to see. We have to reconcile these conflicting cosmic identities. The primitive carbon-rich giant versus the shiny, fresh-faced wanderer that could be hiding a secret. But size is only half the battle, because even a small object is a nightmare if built a certain way. If 1997 NC1 is a solid monolith, it behaves very differently than a loose rubble pile of rocks. This composition debate is why the radar solution coming in 2026 is critical for our survival. We are moving from guessing based on light to seeing the actual terrifying face of this visitor in detail. What we see will determine if our current planetary defense shields are enough, or if we are woefully unprepared. On June 27, 2026, at precisely 1547 Universal C, the Goldstone Solar System Radar will begin its definitive scan of this visitor. This facility represents our most powerful tool for stripping away the cosmic veil, hiding the true scale of 1997 NC1. The GSSR system does not rely on the asteroid's albedo or its ability to reflect sunlight back to us. Instead, it fires high-frequency radio waves into the void, measuring the exact nanosecond they bounce off the asteroid's physical surface. This delay Doppler imaging will give us a resolution so sharp it will be like looking at a photograph from miles away. We will finally settle the debate. Is this a 400-meter regional threat or a 1.6-kilometer global extinction event? Beyond just size, the radar will expose the asteroid's internal skeleton and surface morphology in grueling detail. If the radar shows as a solid, monolithic block of stone, it means we are facing a cohesive and dense mountain of material. Such an object is far more difficult to divert, requiring a massive amount of kinetic energy to nudge off its course. However, if the imaging reveals a loose rubble pile, the tactical situation changes for our planetary defense teams. A rubble pile asteroid is essentially a gravity-bound bag of boulders and dust with almost no structural integrity. In this scenario, using a kinetic impactor like the DART mission's spacecraft could result in a catastrophic failure. Instead of a clean deflection, the impact might simply shatter the cluster, creating a cosmic shotgun blast of radioactive debris. This would transform a single trackable impact point into thousands of uncoordinated strikes across the entire surface of the Earth. The Goldstone data will also identify if 1997 NC1 is a binary system, hiding a smaller moon in its shadow. Binary asteroids are notoriously difficult to predict because the gravitational dance between the two bodies can shift their orbital path. Every centimeter of rotation and every wobble in its spin will be measured to calculate the Yarkovsky effect. This thermal force, caused by uneven heating from the sun, can push an asteroid thousands of miles away from its predicted track. While we watch this object approach from the dark of night, we must also address the danger lurking in the light. The daylight side of our planet remains a massive blind spot that ground-based telescopes simply cannot penetrate. Any asteroid approaching from the direction of the sun is completely invisible to our current detection networks until it's too late. We have seen this before, most notably with the Chelyabinsk meteor that exploded over Russia without any warning in 2013. To solve this, NASA is rushing the development of the NEO-Surveyor mission, set to launch in late 2027. This infrared sentinel will sit at the L1 Lagrange point, looking outward to catch threats emerging from the solar glare. Until that system is online, flybys like the one in 2026 are our only chance to gather vital intelligence. For the amateur astronomers watching from home, the peak visual magnitude will reach 10.5 on the night of the approach. With a 4-inch aperture telescope and dark skies, you will see a point of light moving distinctly against the stars. It is a sobering experience to realize that the tiny speck in your eyepiece is a billion-ton rock screaming past us. This is not just a scientific event. It is a live-fire exercise for the future survival of our civilization. If we find that 1997 NC1 is on the upper end of the size estimates, the stakes for 2026 become truly historic. We are moving into an era where we can no longer afford to be reactive to the chaos of the heavens. Every piece of data from the Goldstone Radar adds a brick to the fortress we are building around our planet. If you value this kind of deep dive intelligence on the threats coming from above, you need to stay tuned to this channel. We are committed to tracking the events that the mainstream media is too afraid to touch or too slow to cover today. Hit the subscribe button and turn on all notifications to ensure you never miss a critical update on our orbital neighborhood. Share this video with those who deserve to know the absolute truth about what is moving through the silence of space. Thank you for being part of this community and for staying informed about our world's future. This is Terra Alerts, signing off for now. Keep your eyes on the skies, because the true story is far from over.